In this video, I'm going to describe some of the basics of electrical current. This is probably your first introduction to this idea after, in a typical physics course, studying what's called electrostatics. That would be situations where the charges were just sitting, usually on maybe a piece of metal or something, and you were describing things like fields and potentials and maybe capacitance. But now we're going to get these charges moving. And the reason we do that is because, practically speaking, when you have moving charges, you can extract some of that energy and do something useful with it, like light up a light bulb or make a motor turn or run a computer. So we're going to see some of the first basics here about current before we get into some of those more specific examples. So the first thing that always can cause some confusion is the difference between the moving charges inside, let's say, a wire versus what we call conventional current. So this is a historical problem going back to like Benjamin Franklin's time, before they really understood well what was causing electrical current. And so they just made this convention that they treated it like positive charges moving through a material. But we've subsequently learned that the actual charge carriers that are moving inside of a metal are not typically positive charges, but they are electrons, those loosely held things inside metals that are really free to move if you give them a little bit of a push from a potential difference. So because of that, we have this difference between what we call conventional current, indicated by the letter I in this figure would be pointed leftward, versus the actual charge carriers inside the metal, which is shown here rightward. So that's just something to watch out for. And just to describe what current is, I'm going to flash over here to the other page. In any piece of metal, you have these random motions of electrons kind of zipping around and colliding with the relatively stationary nuclei of whatever the metal is. But there's no what we call net drift. In other words, every time we have an electron moving rightward, there's probably another one moving leftward, about the same amount. So it's just a bunch of random motions. But as soon as we give a little bit of a nudge, and that nudge comes in the form of a potential difference, so in this case we'll take a slightly different figure, but same idea, we've got these electrons free to move, and if we put this potential difference across the wire, that just might mean connecting a battery to it, then the electrons, in addition to having all those random motions, have this drift. So in this situation here, the conventional current would be clockwise. And that's, again, we're going to indicate that by the letter I. But we're going to look at the electron motion. And so the electrons, you'll see, will be going counterclockwise in terms of their drift. So if we look at any one particular electron, for example, let's just take a look at, I don't know, maybe this one here. You notice where it came from. It at one point was over here, and then it went and banged here and banged in here and banged into here, but it had an overall motion that was leftward. And that's true for this one here. It ends up more leftward. This one ended up more leftward from where it started. This one ended up more leftward. So if we look over a period of time, we'll see most of the electrons have drifted. Now this drift speed is really, really tiny. We're not talking about the actual speed of the electrons as they collide and bang into these things, but the overall drift speed might be on the order of millimeters per second, or perhaps even less than that. So how do we calculate the amount of current that's flowing through something? On the AP reference sheet, my class is an AP class, you will see this equation here, which gets at some of kind of the microscopic details. So current is defined as the number of coulombs per second that are crossing some imaginary area. So you have to imagine that somewhere in the wire, you place this area, so I'm going to put this little circular area in, and then you camp out there, and you're just going to count the number of coulombs that go through that area every second. Think about what would determine the number of coulombs. There's really four factors, and they're all listed here in order. The first factor is the number of charge carriers that you have inside this metal. So this is a number that is just kind of a property of different metals. And so here's a metal that in this much volume, we measure this in like electrons per volume. Then we have 1, 2, 3, 4, 5, 6, 7, 8. But in a different metal, we might have 12. And so you would just see kind of a greater density. I'm not putting these in any particular place, but if we have all those electrons, then we're going to count more of them passing through that little circular area every second. So that's the first factor. Because we're measuring in coulombs per second, not electrons per second, then we need to multiply by the fundamental charge of an electron. That's E, or 1.6 times 10 to the minus 19 coulombs per electron. And then, because we're looking for a particular area, then we've got to multiply by that area. So this would be our area here, the circular shape. We could use the end, the wide end here, which would be a little more area, or we could use this narrow end here on the right, which would be a smaller area. But wherever the area is, that's the area that you put in here. And then the drift speed, and that's that speed that I was talking about before, not of all the random motions, but the general drift of the charge carriers. In this diagram here is showing it to the right, and that would be measured in something like meters per second, or again, remember, we're talking maybe millimeters per second when we actually measure these things. So the product of all four of those is known as the current. Now there's a similar characteristic known as the current density, and that's indicated by the letter J. And actually the name kind of gives this away. If you take the current and just divide it by the area through which that current is flowing, that's what we call the current density. So you could just divide out the A here and you'd see that the N, the E, and the drift speed multiplied together. Something that's, one reason I chose this shape to talk about this is this kind of has this conical shaped here. It's got a wider left side than it has on the right, and so your current density would be different on the left versus the right, because we've got more current kind of packed into a smaller space there on the right, so the current density is higher. Although the current itself cannot be more or less in any one particular part of that wire, because if that were to be the case, we would be accumulating electrons somewhere, and we can't just stockpile electrons. So whenever an electron leaves one little area, it's entering another. So one sort of ground rule is that the current cannot be different when you're flowing through a wire one place versus another place. But if the wire has a different shape, then you can get a greater current density. The last thing I want to point out is something referred to as the conservation of charge. This usually refers to a point at a junction. So here on the left side, I've got this little red dot. We call that a junction, where multiple wires come together. And if we were to take a meter that measures current, we call that an ammeter, and we measure on the left wire here, if we measure 15 amperes, we usually refer to them as amps of current, in that left wire, that's a measure of the charge that's entering this junction. But we can't stockpile charge at a junction, and so that charge has to leave somehow. Now if there were one wire leaving here, then all 15 amps would go out that wire. But the conservation of charge simply says that the total current leaving the junction has to equal the total current entering it. So here we might have a 5 and a 10 leaving, because it has to add up to 15. There's a nice analogy here for this image that I grabbed of water that would meet at a junction. Maybe you got multiple hoses on a hose outside connected together. If you're putting 15 liters per second into the junction, unless this hose is ballooning out, then we must be also having 15 liters per second leaving that. So we would have a measure of the liters per second from each of these hoses has to add up to 15. And this doesn't just pertain to 3 wires. This could be 10 wires all meeting at a junction. But if you add up all the current that's entering and all the current that's exiting, they have to be equal to each other. So that's the idea known as conservation of charge. So I think in 10 minutes here we've kind of hit some of the basics of current and current density, conservation of charge, what drift speed is. That's enough to probably answer most of the questions that you would be asked about in my class or similar ones. So I'll leave it at that. In any more detail, you can probe a little bit more yourself.